Newton's laws of motion play an important role in understanding the forces acting on a body. Let us see in detail how each law is used in understanding the equilibrium conditions. Equilibrium, by definition, is a condition in which all the external forces acting on a body are cancelled out, keeping the body in a state of balance. So, all the forces acting on the body should be arranged such that if we add up all the force vectors, they would sum up to give us a total value of 0. Mathematically, it will simply mean that the summation of all forces will be equal to 0. So, as the forces on a body are all nullified by each other, the body will be in a state of balance, or specifically in a state of equilibrium. Let's use some mathematical equations to understand this better. According to Newton's second law of motion, a body will accelerate if acted upon by some unbalanced force. This acceleration will be in the same direction as net force. So, if an unbalanced net force is acting on a body, it will tend to an acceleration of the body, which means the body will experience a change in velocity. Mathematically, it can be said that the net force is equal to mass times acceleration. But if the body is in equilibrium, it would mean that the net force acting on body will be 0, making the equation as mass times acceleration equals 0. As mass is a constant term for a body and can never be 0, it would mean that the acceleration will have to be 0. So, for a body to stay in equilibrium, either the net force should be 0, or as we just saw, the body should not accelerate. But keep in mind that from the above conclusions, it can also be said that a body moving with a constant velocity, which has 0 acceleration, is also known to be in a state of equilibrium. So, equilibrium not only includes the bodies at rest, but also bodies in a constant velocity. To avoid confusion, the two classifications are used, static and dynamic equilibrium. A body which is at the same position with no movement at all and no forces to act on itself to cause acceleration will be in a state of static equilibrium. Whereas if a body is moving with a constant velocity with no forces to cause acceleration to this motion, then this condition will be called as dynamic equilibrium. We hope.
First condition of equilibrium. A body is said to satisfy the first condition for equilibrium if the resultant of all forces acting on it is 0. Let in the number of forces, F1, F2, F3 to Fn is acting on a body such that F1 plus F2 plus F3 plus so on so forth equals 0. Or summation of F equals 0. The symbol of summation is a Greek letter called sigma used for summation. The equation above is called the first condition of equilibrium. The first condition for equilibrium could also be stated in terms of x and y components of the forces acting on the body as F1x plus F2x plus F3x plus so on and so forth equals 0. And F1y plus F2y plus F3y plus so on and so forth equals 0. Or summation of Fx equals 0. And summation of Fy equals 0. First condition of equilibrium examples. A book lying on a table, a picture hanging on a wall are at rest, and thus satisfies the first condition of equilibrium. A paratrooper coming down with terminal velocity also satisfies the first condition for equilibrium, and is thus in equilibrium. Steps in solving first condition of equilibrium problem. First, draw the free body diagram or FBD. Second, resolve forces into their components, always considering the direction of these forces. Third, get the sum of all the forces along the x-axis. Remember that this summation is equal to 0. Fourth, get the sum of all the forces along the y-axis. Remember that this summation is equal to 0. And lastly, solve for the unknown force. Static equilibrium. Static equilibrium means equilibrium of objects that are at rest. Dynamic equilibrium. Dynamic equilibrium means equilibrium of objects that are moving with constant velocity.
What force is required to produce an acceleration of 40 meter per second squared and a cricket ball of mass 0.5 kg. Now let me highlight the given data and the problem. What force is required to produce acceleration of 40 meter per second squared and a cricket ball of mass 0.5 kg. So we are given three variables. Find force. The values of acceleration is 40 meter per second squared and the mass is 0.5 kg. So here I write F, here I write A, and here I write M. Now according to Newton's second law of motion, F is equal to ma, where F is force, m is mass, and a is acceleration. Thus F is equal to mass m is 0.5 kg and acceleration a is 40 meter per second square. Hence, as a result, F is equal to 20 kg meter per second square. We know that 1 kg meter per second square is equal to 1 Newton. Hence, F is equal to 20 Newton. This means if we exert force F is equal to 20 Newton on a cricket ball of mass 0.5 kg, this 20 Newton force will produce 40 meter per second square acceleration and 8. The second problem is find acceleration produced an engine force of 3600 Newton and a car of mass 600 kg. Now again I will highlight the given data. Find the acceleration. So we have to find acceleration in this numerical. Secondly, the engine force of 3600 Newton. So we highlight force F of 3600 Newton. Thirdly, in a car of mass m of 600 kg. Here in this numerical, we are again given three variables, F, m, and a. According to Newton's second law, F is equal to ma. We need to find the acceleration a of the car. So shift this m from the right hand side to the left hand side. A is equal to F upon m. Now plug in the values in this equation. A is equal to 3600 Newton upon 600 kg. As a result, we get 6 meter per second squared acceleration. Hence, 3600 Newton will produce an acceleration of 6 meter per second square and a mass of 600 kg. The third problem is calculate the force required to stop a car of mass 1400 kg in 2 seconds if it is moving with velocity of 10 meter per second. Now again I will highlight the given data. Firstly, calculate the force F and highlight it. Secondly, to stop a car means that final velocity Vf of the car will be 0. Thirdly, mass m is equal to 1400 kg and highlight it, and time 2 seconds, so it is time t and highlight it also. If it is moving with velocity of 10 meter per second, this is initial velocity Vi and also highlight it. There are 5 variables given in this problem and we have to find force F to stop a moving car. According to Newton's second law, F is equal to ma. Here the mass of the car is 1400 kg. Now what about the acceleration A of this car? To find the acceleration A of this car, we are given initial velocity Vi, final velocity Vf, and time t of the car. So the acceleration A of this car is equal to Vf minus Vi upon time. Now I will put this value of acceleration in the Newton's second law. Thus F is equal to m into Vf minus Vi upon time. Hence, plug in all these values in this equation. F is equal to mass, m is equal to 1400 kg, and to final velocity Vf, which is 0 meter per second, minus initial velocity Vi, which is 10 meter per second, upon time, which is equal to 2 seconds. As a result, we get F is equal to minus 7000 Newton. Here, the negative sign shows that this force 7000 Newton is a retarding force. It means this force stops the car. Lastly, find acceleration produced in a truck of mass 900 kg if the horizontal engine force is 500 Newton and the friction force is 200 Newton. Now read it for highlighting variables. Find acceleration. So we have to find acceleration A and highlight it. Secondly, in a truck of mass M 900 kg and also highlight it. Thirdly, if the horizontal engine force F is 500 Newton and highlight it. Fourthly, the friction force small f is 200 Newton and highlight it. Now let me draw a freehand diagram so that you could understand it in easy way. Let's consider a truck. Let its mass is 900 kg. Let the horizontal force F is equal to 500 Newton is acting in this direction, while the friction F is equal to 200 Newton, being opposite force, acts in the opposite direction. So the net or the resultant force on the truck is 300 Newton. And remember this 300 Newton force as a resultant force. Now this net force of 300 Newton produce acceleration A in this truck of mass 900 kg. According to Newton's second law of motion, F is equal to ma. We will shift mass m from the right hand side to the left hand side. Hence A is equal to F upon m. Now plug in the values in this equation. A is equal to the net force F on the truck is 300 Newton and the mass of the truck is 900 kg. So 300 Newton upon 900 kg. As a result, A is equal to 0.33 meter per second squared. So this 300 Newton net force will produce 0.33 meter per second square acceleration in the truck.
Applying Newton's second law of motion. The second law discusses motion with acceleration. This can only happen if there is a net force. Thus, summation of F is not equal to 0, and the net force is equal to the product of mass and acceleration, given by the equation, summation of F equals m times a. There are three possible ways to have a net force equal to m times a. Case 1. Summation of fx equals m times a sub x. And summation of fy equals 0. Case 2. Summation of fx equals 0. And summation of fy equals 0. Case 3. Summation of fx equals m times a sub x. And summation of fy equals m times a sub y, where x is acceleration along the x-axis and a is acceleration along the y-axis.
Imagine you've got a tennis ball attached to a piece of string, and you start swinging it in circles. Whoa now, watch out for your buddy! Let's take a closer look at the fascinating physics of this simple action. You've probably heard of Newton's second law of motion as it relates to objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force. Now back to our spinning ball. For objects undergoing circular motion, the net force on the object is called the centripetal force. It's a weird sounding word, but it's Latin for the phrase center seeking. It's named centripetal because the centripetal force always points to the center of the circle. The ball has a tangential velocity, so if you suddenly cut the string, it would fly off in whatever the tangential direction was at the moment you made the cut. But assuming you don't cut the string and you keep swinging the ball's tangential velocity is constantly changing directions. This means the ball is accelerating, and the reason it's accelerating is due to the centripetal force. The centripetal force acting on the ball is constantly directing the ball towards the center of the circle, your hand. This, combined with the ball's velocity, keeps the ball swinging in a circle. The same centripetal force that keeps the tennis ball swinging in a circle also keeps roller coasters on the track as they go through a loop-de-loop. So the next time you're having a blast on a roller coaster, you can thank the centripetal force.
We've examined a lot of linear motion up to this point, whether horizontal, vertical, or at some angle. But there are a lot of objects that follow circular paths of motion. This type of motion is accompanied by an entirely different set of equations, so we have to learn these if we want to approximate the motion of the planets as well as a wide variety of earthbound objects. Consider a Ferris wheel. As the wheel turns, the cars exhibit circular motion because they revolve around a single axis of rotation, which runs through the center of the wheel perpendicular to the plane that contains it. The cars move around this axis with a constant radius, so they trace a circle as they move, since a circle is the set of all points equidistant from some central point. To describe the speed of the car, it is common to discuss the tangential speed because the inertia of an object causes it to try to maintain a straight line path. This is the speed of the car along the tangent line at a particular instant. If this tangential speed is constant, we will call this uniform circular motion. The tangential speed will depend on the distance of the car from the axis of rotation. If you place a sticker on the wheel very close to the center, it will complete one revolution in the same amount of time as one of the cars. But the sticker will travel just a short distance that you could trace with your finger, while the car travels much farther, all the way along the edge of the wheel. Since speed is distance over time, a shorter distance covered in the same amount of time must mean a slower tangential speed. This seems counterintuitive, since the wheel is one object, but that's why we can also discuss angular velocity, which we will learn about later. The uniform circular motion of the car happens because of a constant centripetal acceleration towards the center of the wheel. At any given moment, the car has a velocity vector that is tangent to the wheel, and while the magnitude of this velocity will not change, the direction is constantly changing, and any such change in velocity can only happen due to some acceleration. The centripetal acceleration will always point towards the center of the wheel, which will in turn continually pull the direction of the velocity vector towards the center of the wheel. This is what produces the circular motion, as though the car is always trying to move towards the center of the circle, but never makes it there because of its tangential speed. Centripetal acceleration is given by tangential speed squared over the radius of the path, so this value would increase if the car were to move faster and if it were to sit closer to the center. We know from Newton's second law that if an acceleration occurs, there must be some force present to produce it, and centripetal acceleration is generated by the centripetal force. Centripetal force is simply centripetal acceleration times the mass of the object, since F equals ma. So we can describe centripetal force by simply adding the subscript c on force and acceleration, or it can be given by m times tangential speed squared over the radius of the path. This represents the force that must be applied to produce the circular motion, like the amount of force that must be applied to spin a ball on a string in a circle around your head. If this centripetal force that points towards the center, perpendicular to the tangential velocity, were to suddenly vanish, in the event that you were to let go of the string, then the object would simply move along the tangent line at the precise moment of release, since there would no longer be any force pulling the object towards the axis of rotation. So centripetal force is the force pulling an object inwards towards the axis of rotation during circular motion, and it can take the form of tension from a string, gravity exerted by massive objects, or static friction from the road when a car navigates a curve. But when you are on a rotating object like a merry-go-round, you feel yourself getting pushed outwards. This is often referred to as the centrifugal force, implying that it is the reactionary force to the centripetal force. But in actuality, this is not a real force. The sensation that is produced on the merry-go-round is simply due to the inertia of your body attempting to maintain a straight line path of motion. Inertia is not a force, it is just a result of Newton's first law. You are not physically part of the merry-go-round, but if you hold on tight enough, the resulting frictional force will cause you to follow the same circular path without any problem. If you are seeking a thrill and decide to let go, inertia will outweigh the centripetal force and you will fly off the side, hopefully onto some soft grass. Let's check comprehension.
Centripetal force. According to Newton's second law of motion, acceleration is produced by a net force. The net force and the acceleration must be in the same direction. If applied to uniform circular motion, the acceleration becomes the centripetal acceleration and the net force. Since it is also directed toward the axis of rotation, it also becomes the centripetal force. Centripetal force can be defined as the net force on an object that maintains the object's circular path, and it is directed toward the center of the circular path. Mathematically, the centripetal force is given by the equation F sub c equals m times a sub c, where F sub c is centripetal force in Newton, m is mass in kilogram, and a sub c is centripetal acceleration in meter per second squared. When the distinction between the tangential speed and angular speed is applied, the equation can be written as F sub c equals m times v squared, divided by r, or F sub c equals m times r, times w squared, where v is tangential speed in meter per second, r is radius in meter, and w is angular speed in radians per second. The centripetal force is the force that maintains the circular path of the object. If the centripetal force is zero, the object will move in straight line. Example. What is the centripetal force of an 8,000 kilogram train, running at a speed of 27.8 meter per second, and rounding a curve with curvature radius of 150 meter? Given, m or mass equals 8,000 kilogram, r or radius equals 150 meter, v or speed equals 27.8 meter per second. Find F sub c. Solution. F sub c equals m times v squared divided by r, equals 8,000 kilogram times 27.82 meter per second, divided by 150 meter. Centripetal force equals 41,218.13 Newton. An example of the occurrence of centripetal force happens to a runner who, when going around a curve, leans inward to obtain the centripetal force that causes him to turn. The roadway must exert an upward force sufficient to sustain his weight, while at the same time, it must supply a horizontal centripetal force. If the roadway is flat, the horizontal force is entirely frictional. In that case, the frictional force may not be large enough to cause a sharp turn when the surface of the roadway is smooth. If the roadway is tilted from the horizontal, a part of the horizontal force is still supplied by friction, but the remainder is a result of the reaction of the surface. If the angle banking is properly selected, the force the roadway exerts is perpendicular to its surface and no frictional force is necessary. Rotational kinematics. Kinematics and Newton's second law of motion provided the basis for analyzing motion from one place to another, and the forces that cause motion to change. Here, we restrict our attention to objects moving in a circular path at constant speed, such as balls swinging in a horizontal circle at the end of the string, the moon circling the Earth, or a race car moving at constant speed around a circular tract. Force is needed to keep an object at constant speed using Newton's second law. The force pulls the object toward the center of the circle, however, it does not change the object's speed, only its direction of motion as it moves in a circle. Examples of these forces that exert an inward force in an object as it moves in a circle are Earth's gravitational pull on the Moon, and the tension force of a string pulling on a ball swung at its end. Objects tend to rotate on an imaginary straight line in the middle known as an axis. When an object turns about an internal axis, or the axis within the object, it is called rotation. When the object turns about an external axis, the motion is called revolution. Planets in our solar system are undergoing both rotation and revolution. An example is Earth, which rotates along its axis and revolves around the Sun. A lot of thrill rides apply the principle of uniform circular motion. One of these rides is the merry-go-round. If we look closely at a merry-go-round, the horses that are farther from the center will have to travel longer distance than the ones in the middle. Tangential speed. Speed is defined as distance traveled in a given time interval. Applying this definition, it is clearly seen that the horse on the outermost part will cover a large distance than the ones in the middle. Therefore, the outermost horse will have greater speed than the ones in the middle part. Any two horses that have different distances from the center will have different speeds. This speed is what we call tangential speed. This is the motion that is always tangent to the circle. Another name of tangential speeds is instantaneous linear speed at that particular point on the circle. Rotational speed. There is also another speed involved in a merry-go-round that does not consider distance. This speed counts the number of rotations done in a given time interval. This speed is called the rotational speed or the angular speed. Any part of a rotating object will have the same rotations in any given time. Whether the horse is in the middle or outermost part, the rotational speed will be the same. Rotational speed is measured in terms of radians per second. Rotational speed. Rotational speed or angular speed measures the change in the angle per unit time of rotating object. For a complete rotation or 1 revolution, the angle covered, theta, is equal to 2 pi radians and the time measured is called period, t. So, the rate at which the angle changes per unit time is equal to omega equals theta divided by t, equals 2 pi divided by t, where omega is the rotational speed or angular speed in radians per second and t is the period in seconds. If the tangential speed of the object does not change, then the object is said to be undergoing uniform circular motion. However, an object moving in a circular path is constantly changing due to a change in the direction. If there is a change in velocity per unit time, then acceleration is produced. For uniform circular motion, this acceleration is called centripetal acceleration. Centripetal acceleration is still the change in velocity per unit time, but it is always directed toward the center of the circle or the center of curvature. Centripetal means center-seeking, so centripetal acceleration is a central-seeking acceleration. The tangential speed and the tangential velocity have the same magnitude.
To summarize our lesson for today, a force is a vector quantity that means either a push or pull acting on an object as a result of its interaction with another object. Forces can be classified as contact forces, which require physical contact between objects, or non-contact forces, otherwise known as action at a distance forces or field forces, which do not require physical contact to have any effect on the other object. Examples of contact forces include applied force, normal force, air resistance force, frictional force, tensional force, and spring force. Meanwhile, non-contact forces include the following examples: gravitational force, electrical force, and magnetic force. The sum of all forces acting on an object is called the net force or resultant force. Unbalanced forces change the motion of an object, whereas balanced forces do not. A free body diagram is a diagram showing all the known and unknown forces acting on an object, indicating their magnitudes and directions. Mass is a measure of an object's inertia. The greater the mass of an object, the lesser its acceleration when pushed or pulled by a force. Mass is also an indication of the amount of matter which comprises the object. An object's weight is the gravitational force exerted on the object due to its gravitational attraction to other masses such as Earth's surface. Near the Earth's surface, an object's weight and mass are related by the equation weight is equals to mass times acceleration due to gravity. Friction force opposes the motion of one's object across another surface. If an object is not moving, it is supported by a static friction. If the object slides across a surface, it is opposed by a kinetic friction force. A measure of roughness of two surfaces is indicated by the coefficient of friction. Friction force is computed using the equation frictional force equals coefficient of friction times the normal force. Newton's laws of motion relate an object's motion to the forces acting on it. It was formulated by English physicist and mathematician Sir Isaac Newton. Newton's first law states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an external net force. This law is also known as law of inertia. The second law, or otherwise known as law of acceleration, states that unbalanced force acting on an object will cause the object to accelerate in the direction of the force. The acceleration is directly proportional to the vector sum of the forces acting on it and inversely proportional to the object's mass. While the third law states that for every action, there is an equal and opposite reaction. The first condition of equilibrium states that for a system to be in equilibrium, the net force must be equal to zero. For a net force to be zero, the components of a net force must all be zero. There are two kinds of equilibrium, static and dynamic. Static means equilibrium of objects at rest, while dynamic equilibrium means equilibrium of objects that are moving with constant velocity. The centripetal force is the force that maintains the circular path of the object. Tangential speed is the motion that is always tangent to the circle. When the tangential speed of an object does not change, the object is said to be undergoing uniform circular motion. However, when the tangential velocity is constantly changing, due to a change in direction, acceleration is produced. For uniform circular motion, this acceleration is called centripetal acceleration or center-seeking acceleration.
Activity A. Directions. Select the letter of the correct answer. 1. An object moving in uniform circular motion has a constant blank, but a changing blank. A. Speed, velocity. B. Velocity, speed. C. Acceleration, speed. D. Force, speed. 2. What is the name of the force that keeps an object in circular motion? A. Centripetal force. B. Centrifugal force. C. Gravity. D. Tension. 3. The force of gravity pulling down an object is called blank. A. Mass. B. Weight. C. Physical change. D. Resistance. 4. What is the unit of measurement for weight? A. Grams. B. Newtons. C. Pounds. D. Kilograms. 5. F equals m times a, shows the relationship between force, mass, and acceleration. A. Newton's first law. B. Newton's second law. C. Newton's third law. D. Ohm's law. 6. Centripetal acceleration always points blank. A. In the direction of the object's motion. B. In the opposite direction of the object's motion. C. Towards the center of the circle. D. Towards the outside of the circle. B. Directions. Solve the following. 1. Your shopping cart has a mass of 65 kilograms. In order to accelerate the shopping cart down an aisle at 0.3 meter per second squared, what force would you need to use or apply to the cart? 2. A small child has a wagon with a mass of 10 kilograms. The child pulls on the wagon with a force of 2 newtons. What is the acceleration of the wagon? 3. What is the acceleration of 2,000 kilogram truck if a force of 4,200 newton is used to make it start moving forward? 4. What is the acceleration of a 0.30 kilogram ball that is hit with a force of 25 newton? 5. What is the mass of an object that requires a force of 30 newton to accelerate at a rate of 5 meter per second?